Today's live stream on LinkedIn is with Greg Law from Undo. Thank you for coming, Greg. I'm looking forward to your presentation about time travel debugging. Let's take it away.
Excellent. Thanks, Jens. Thanks for having me. Yeah, so actually, if anybody's got any questions, yeah, do fire them off during the talk. I'm quite happy. Actually, always happiest if we take a little bit of a tour around and do it kind of in an interactive style. So yeah, questions are good. Right, let's crack on. So this chap, Sir Maurice Wilks, I think he has as good a claim as anybody to being the world's first professional programmer, right? The first person to write code on what you'd recognize as a computer, a stored memory, stored program computer, and which is doing it to do a real thing, right? Rather than just like prove this prototype machine actually worked. He was actually solving a real problem. So I think, as I say, good a claim as anybody to being the world's first programmer. And he says in his memoirs that he remembers that moment when he realized that a good part of the remainder of my life was going to be spent finding errors in my own programs. And that resonates with me, I've got to say. And I think with a lot of people, that moment when you start programming, you kind of get bitten by the bug, just to use some confusing terminology, but and you realize it's really hard to get it to work. Now, of course, the term debugging, bugs and debugging hadn't been invented at this point. This was invented by Grace Hopper when she found in the back of her machine an actual bug, a moth that was the cause of the failure that they were investigating. Actually, that story is not quite true. So I never pass up the opportunity to be a pedant. And it turns out that debugging predates that by a long way. And actually, you can see here on the right is a copy of a picture of the logbook where that instance happened. And you can see underneath where the moth is sticky taped into the logbook, you can see underneath it says, first actual case of a bug being found, right? So that doesn't make sense, right? First actual case of a bug. That doesn't make sense unless it's already a term, and this is basically a joke. It's humor, right? And in fact, the term debugging goes back at least 50 years before. It turns up in Edison's logbooks when he's debugging his inventions. But I think it really became popularized with computer programming because it was just such a big part of programming, right? I mean, if you think about it just for a moment, how many lines of code do you think would you back yourself to write and have it work, have it work first time? 10 maybe if it's quite simple, and you really think 20. I don't know, maybe you're a better programmer than I am, but I in my experience, 10 lines of code doesn't work first time in practice, right? And even more so, actually, I think how many lines of code can you change and have it work first time? I think that number is less than one. It's really debugging dominates. In fact, programming is sometimes said there's two parts to programming. There's bugging and debugging. There's writing the code, typing the code in, and making it work. So computer's hard. Debugging is just this bit that completely dominates software development, but we don't really talk about it very much, right? It's just kind of accepted. It's a bit of a dirty secret, perhaps, we just kind of get on with it. But another good quote here from another very smart man, Brian Kernighan, says, you've probably heard this, is quite a well-known quote. It says, everyone knows that debugging is twice as hard as writing a program in the first place. So if you're as clever as you can be when you write it, how will you ever debug it? Now, I think what Kernighan's really saying here is, keep it simple. Give yourself, margin for error. Don't try and be as smart as you can be. But I think there's an interesting corollary to this, right? If you take this as true, and I think it is true, then what this means is that debuggability is the limiting factor in software development, right? So whatever your metric for good is in your program, maybe it's how fast it runs or how extensible it is or how quickly you can write it or how small it is, whatever your metrics for good, then if the program is twice as debuggable, then it can be twice as good, right? Because it's this limiting factor. So I think we don't spend nearly enough time, thinking about this and investing in tooling and skills and everything to make us better. And in practice, you think about how do we debug most of the time, right? Given that if most of the programmers' time is spent debugging, what are they doing? Well, maybe we've got pretty cool tools these days, like the dynamic checkers, like Valgrind, or the sanitizers, very handy and sometimes very useful, right? But I'm not talking here about how often do you run this, like inside your CI or something. Maybe you've got some checkers in your CI pipeline. That's good practice. We certainly do at Undo, and very useful they are too. But I'm talking about debugging. I'm talking about my program's got a problem. It's not doing what I wanted it to do, and I'm trying to figure out why. Okay. And in that process, maybe I suspect some Stack Overflow or something, and I'm going to run it through Valgrind and see if I get, see if it gives me a clue. But for most people, not very often, right? This is like, I think you'd measure this in like a few times per year tops. Most people actually, I suspect it's a few times, per decade or something, right? So very useful, but not used that much. Now, debuggers, GDB or Visual Studio, whatever your favorite debugger is, I think get used more frequently, but still actually infrequently. I think for most people, once a month, maybe, if that, right? A few times a year. It depends. Some people use them as a matter of course, but most people, I think, in my experience, most people turn to the debugger relatively infrequently. What do programmers do every single day? They add more printfs, right? We add printf, we run again, we get some more information. And, this really hasn't developed either, from the first programs that were being written, or indeed from the first time we programmed, right? If you can remember back when you first started programming and it didn't do what you wanted it to do, you start adding printfs. And that's what most of us do most of the time. And why is that? Well, I think there's a couple of reasons for it. And one, actually, slightly provocatively, perhaps, I think there's an element of laziness to this, right? Add the printf, I recompile, I run it again. Okay, get a bit more information. Now I have to add another, but not enough. But I've got a clue, so I add another printf and another printf. And I can kind of feel good about myself in that I'm working hard, right? I'm not slacking off. I'm working hard, but I'm not really thinking hard. I'm just in this kind of going through the motions almost. And I think it's kind of the programmer's equivalent of just reading email. Right? You can just read your email and feel like you're being efficient, but actually you're not really doing anything. Printf debugging can be like that, I think. But I don't think that's the whole story, right? I think there are other reasons why printf debugging is so popular. And I think a large part of it actually is when we're debugging, it's really it's a process of trying to think and figure out how did that happen, right? I don't mean like how did that happen or how did that happen. I mean I had some expectations of what my program was going to do when it ran, right? And at some point, reality diverged from those expectations and I got a different result. Maybe I got an assertion failure, maybe it crashed with a segv, maybe it gave me bad results or ran too slowly, such as the program didn't behave in the way that I expected. And the process of debugging, of course, is thinking back from where I observe the difference back to where is the root cause, where does reality diverge from my expectations. Of course, usually it's more like that. And it can be that you go through a very kind of circuitous route, if I can say that, to you have to track back in some unexpected ways. And this is really part of what makes debugging hard, right? Often the bug itself happens a relatively long time, might be just milliseconds, but a long time in computer world, the bug between the bug and you noticing. This is why assertions are very useful, right? Because they basically, they reduce that window and they reduce that time. The longer you have to think back in time, the harder it is. But printf is good, right? Because printf tells you what happened. It's exactly what it's doing. The debugger doesn't do that, right? I mean, and the dynamic checker, not really either. I mean, dynamic checker sort of says, okay, this set of, I've got a canned kind of set of bad things, and none of them happened, right? Or maybe, yeah, one of my fixed set of bad things happened here. But it doesn't tell me what the program did, right? In the way that printf does. And even the debugger, not really very usefully. I think you can, sometimes I think you can think of the debugger as, I sometimes think of it as a bit like the film, the cinematography style that got popularized, I think, by the first Matrix film, where everything freezes and then the camera kind of pans around 360 degrees, and you can see the bullet kind of in midair as it's flying through the air from different angles. That's what a debugger does. It lets you freeze time and lets you look at anything, any piece of your program state. You can look from any angle at what's going on, and you can maybe step forwards, one frame, very slow motion, or you can just run forwards again at full speed. But it doesn't tell you what happened, right? It tells you what's happening. So printf's kind of good, but obviously printf is, the limitations of printf are pretty obvious. In particular, usually you don't print what you need. You're printing out, you're necessarily printing out a tiny fraction of everything that the program has done, right? The computer's issuing billions of instructions every second. Even if your program is being very noisy and printing, 100 messages, 1,000 messages a second, it's still a tiny fraction of what's going on, right? So you have to get pretty lucky or be pretty smart for what you need to be in that log. So what we want is both worlds. We want the view of what happened, and we want the ability to see everything, to move that camera around 360 degrees, look at any angle, any piece of state. And that's what we're going to get to. So billions of instructions a second. We're looking for that, the ultimate needle in a haystack challenge. What we want is the equivalent of a metal detector to help us. And that's what time travel debugging is, right? It gives us the ability to wind the tape back to any point in the program's execution, literally any line of code that executed, and see any piece of state. This here you probably recognize. This is from H.G. Wells' The Time Machine, the film of. And unlike many of the later time travel sci-fi stories, which are kind of interested in what happens if I can go back in history and change time, in The Time Machine, he's more kind of passive, right? He's an observer in what's going on. And that's what we're talking about here. So we're not talking about the ability to go back in time and change something and run forward on a new timeline, because that famously, there are paradoxes when you try and do that, right? And everything gets very complicated, and it's actually not what you want. What you want is to be able to know, how did that happen? So being able to go back in time and observe is exactly what you want, and exactly what Time Travel Debugger gives you. So let's show what this looks like in practice. I'm going to show a couple of examples. Let me try and get text nice and, whoopsie, I didn't do what I wanted. Get text nice and big.
A question from Leonard Katova. What languages do we, or could you use with those tools we are presenting today?
I think time travel debugging is I think it's an idea whose time has come, and it's available, right? I mean, there's quite a few languages that are supported. So C++, absolutely, and that's kind of the context of this meetup, right? C and assembly code, anything actually that GDB can debug can be time travel debugged. So Rust, Fortran, Ada, and there's also time travel debugging solutions for Java, for C# on the Windows platform, and for and even for JavaScript for front end, web applications. So there's a number of different languages now that have support for time travel debugging. Not everything, but chances are there's something out there that will work for you. I'll give it I've got a slide later on where I'll give a brief taxonomy of those again. So that should hopefully make it a bit clearer. But let's show a little demo of this then, right? So I've got here a program, a little bubble sort program, and it looks like this, right? It's a classic bubble sort implementation, and the main function just takes an array, puts random data in it, and then sorts it, and that's it. And this is the program here. Doesn't print anything on the screen, just gets some random data and sorts it. But look at that. There's a bug. There's there's an intermittent bug here. Actually, this failed pretty early on. It usually takes a few more goes than that. But okay, I've got an intermittent bug, and it's created a core file. So let's have a look. What's that core file? So that's this one here. So what do? We load that up into GDB, right? And what do we do when we load a core file into GDB? Almost always the first thing you do when you load a core file into GDB is you ask for a backtrace, because what you want to know is what happened? How did I get here, right? Sometimes you get that kind of experience. Okay, my backtrace is garbage. I do have debug information in this. I know I do, but I've got a smashed stack. Now, that obviously is a thing that can happen. More often when you get a core file and you get a backtrace, the backtrace works, but it doesn't contain the information that you need, because it's a tiny sliver. It's a tiny sliver of breadcrumbs of what the program did. So you can see it, perhaps a dozen functions that it's been through, but it doesn't tell me everything that happened. So if I'm lucky, I load my core file, backtrace. Oh yeah, look, I didn't check that pointer for null or something. But usually it's, if I'm usually the best I'll get is a clue, and often I just get, well, that doesn't make any sense. That stack trace looks like either impossible, that should never happen, or looks fine. But the core file, interesting thing about what the core file is here. So the core file is a snapshot of the program state, all of the states, the threads and the registers and everything, but a snapshot of the program state at the point it crashed, at the point it terminated, right? If I get a recording, a time travel recording, it's like that, except it's got that full program state for all of history. So let's try and do that. So I'm going to use here a tool called RR. RR stands for Record and Replay. It's an open source tool. It's packaged with most distributions these days, so it's probably there on your system. And I can record it like that. I haven't rebooted my machine since I last gave this demo, so it does rely on the performance counters being available. So we have to set, so what are we going to do? Let's set echo 1 to sudo t. That's just do my password. I think I might have missed that again. Oh, it's hard to do your password when someone's watching, isn't it? Right. Okay. So I've now set up the system so that it's got the necessarily precise performance counters that RR depends on. So let's have another go. And oh, look at that! It failed first time, but it usually doesn't, right? So, but that one did fail first time I ran it. So it's saving its execution trace there. So RR replay that. Okay, and what that does is this gives me, look, I'm at underscore start here, so I'm right at the beginning of that program's execution, and it's a recording of everything that happened. So I'm just going to continue this to the end. Okay, and here we are when we've got our segfault. And if I go backtrace, yeah, this, okay, slightly different backtrace, but still messed up. So just like before. But I've now got time travel. So what I'm able to do is reverse step I. Okay, so step I in GDB steps you forward 1 instruction. Reverse step I steps you back 1 instruction. Okay, I just need to do that. That's when the seg fee was received. So I just need to do that once again. And here I am. Now I've got a backtrace. I'm actually only at main. I'm going to go layout source so we can see a little bit more easily what's going on. So look, I'm at the return from main. This is kind of, I suppose, vaguely what you'd expect, right? If I've ruined the stack. Let's look at the disassembly code here. So oh, that wasn't a very good view. I'm actually going to go back into that, just look at the disassembly. So here's my main function, and here's, you can see from GDB, here I am. This is the this little arrow here tells me this instruction. I am indeed at the ret instruction. So ret on x86, it will take what the stack pointer points to and branch to that, right? So it's a full descending stack. So if I print, there are smarter ways to do this, but this will do. If I print the stack pointer, print what's at the stack pointer, that's what's at the top of the stack. So if I were to try to look at that memory, that's where we're returning to. Yeah, it's a bogus address, right? I'm trying to return to, it looks like it might be hex or some ASCII or something, that, rather than the pointer. Whatever it is, it's not a valid address. Right, so I've got garbage on my stack, right? Someone's written into my stack, and I need to know, like, when did that happen? Now, this is a very, very small program just for demo purposes, but I'm sure you've been there before with a more real program, and it's really hard to know. But what I can do here is, so stack pointer is that. So if I put a watch point, and I'm going to watch the top of the stack, I'm going to watch that address. Okay. Now, watch point, sometimes called a data breakpoint, what it lets you do is run the program until data changes, which is, it's a niche feature, can be useful sometimes. With time travel debugging, this is like a killer feature, right? Because you might be one step ahead of me or behind me here. What I'm going to do is not continue until the data changes. I'm going to reverse. I'm going to run backwards until the data changes, and that will be the line of code that Roast recently wrote to my stack, right? That's what I care about. So reverse continue. Gosh, right, I've gone back in time. I've gone back here, look, what's going on? Well, we're writing into this array that's writing into my array on the stack, so that's not like super good surprising. We're writing into the ith element. I is 35. That is kind of surprising because array is only 32 elements long. And of course, the bug here is that I've got percent size of, which is, of course, bytes, the size of the array in bytes, not the size of the array in elements. So I'm just writing over the end of the array. And that happens to be on my stack. And so when I return, I'm returning to garbage. So tiny little program. You could probably just stare at the lines of code for 5 minutes and spot this. But you can see, hopefully, how that will be very, very useful in much larger programs with much more real kind of bugs. And I think an important point to make is most of these time travel technologies do scale. I mean, RR was basically invented to debug Firefox, and does work on programs of that scale. Our own stuff, Live Recorder, we work with programs that are sometimes terabytes, literally terabytes of working set, and literally days of runtime in extremis, right? And modern time travel debuggers do scale. The Microsoft time travel debugger is used extensively by Microsoft, by the core team, by like the SQL Server team and the Office team and people like that. So, and you can see hopefully how that's very, very useful. I want to show you one more demo now. It's still a bit of a toy program, but it is could give you a sense of how it could be usefully integrated into the workflow. So I'm going to switch to. Okay, right. So sorry about that.
Greg,
yeah,
there's one question, like, is like time travel debugging as a package, comes that with GDB automatically, or is RR the tool you just showed? Do you need to install that?
RR is a separate tool. There is some time travel debugging in GDB automatically, but it's really good only for very small programs. It's very, very slow, and it's not super well maintained. So there's a thing called process record. So I can just start GDB normally, and I'll show you very quickly. So if you start GDB normally, like this, start, and I can enter this command record. And then once I've done record, I can do step, and I can go reverse step. Okay. So you can just do that. You can just do that, but it's very slow and not super well maintained. So if you do any sort of modern like AVX type instructions, which libc will do, it will stop at that point. So you probably want RR or Live Recorder, or one of our sort of separate tools. Time travel debugging is built into the Microsoft WinDGB WinDBG product. So it's a bit more kind of standard there. Okay. All right. So this is a pull request on our internal GitHub at Undo that I made, and like every pull request I've made, I ever make, it has some failures. So because I can't write more than a few lines of code without creating a bug, as discussed. This one was deliberate, but so made a pull request. It kicked off some tests to Jenkins, as normally happens, right? This is all pretty standard. So some of those tests failed. I can click through here, and I can look at the test results, and here we have the log of that test failure. So this is like very normal, right? I mean, the details are different, but the concept probably you're familiar with. So here's the program. It hits some logs. Oh, look, here's an assertion failure, and then there's some more stuff, and there's back traces. But you know what? I'm not going to go through all of this because I can tell you there's not enough information in here to root cause this bug. Sometimes when I get a failure in Jenkins, I can look in the log and I get enough information to root cause the bug at that point. But that is not the common case, right? But what we have here in this Jenkins is this thing called observatory. So I'm going to just follow that link. And this has got a bunch of artifacts. Some of these are recordings. So here's a recording of that test that failed. So click on that. It's going to launch it up. What it's going to do is it's going to do quite a lot of work behind the scenes. It's going to provision a machine, get the replay session on that machine, and it's going to get the right version of the source code, that Git version that was associated with that run. It's going to get any artifacts from their logs, things like that. And critically, it's going to load up this recording. And this will just take me a few seconds, and it's going to dump me in there. So just by that single click, 30 seconds, the system goes off and does what it needs to do to get everything together so that I don't need to do what you normally need to do when investigating a test failure, which is the first thing you tend to need to do is try and reproduce it. Well, I don't need to reproduce anything here. I've just dived straight into the recording. So here I am. So an exception has occurred because, this assertion has failed. So it's saying square root cache is 0 and the correct value is 15. So hence the assertion has failed. This, by the way, if you might notice, this is VS Code. This is a VS Code interface running in the browser. So I've got my call stack here on the left. Actually, what this shows me is this is a multi-threaded program, lots of threads. Thread number 10 is the one where the assertion has fired. And actually, you can see here from the call stack, so VS Code is kind of nice and puts you at the last line of code, where you have debug information for the source code. But it's actually deep inside the C library because that's what happens when an assertion fails, right? You end up inside abort and then inside raise. So that's fine. We've recorded all of that. We can record down to the instruction level. So I'm going to hit this button here, this reverse step out kind of uncall button, and watch the stack as I do this. And it's kind of like popping up the stack. Well, you're probably thinking, so what? Because you can always do that even in a core file, right? But it's not the same as popping up the stack in a core file because it's really unwinding the execution. All my globals and everything else go back to what they were. It's not a guess about where I've been. That really is here. As I saw in the last demo, I can do that when I don't have a stack. But anyway, I've reversed back into my code here, and we can see we've got all the data here. And now I'm going to do, so this is like super cool here, right? So I've got my reverse step, just like the step buttons that you're probably familiar with. This has got a reverse step. When I click this, we're going to go back one line, right? Exactly one line. And by the way, watch the data up here in the top left because that will change as well. So, right, there you are. So I've gone back a line. Only one piece of data changed, one variable changed because that's the only one that got changed there. That's where it's correct. Now, what's going on? So let's just have a bit more look at what's going on. So it's got this cache calculate. I've passed it in number of 255 and it's returned 0. And what it was supposed to return is square root correct. It's supposed to return 15. It's supposed to return a square root, right? And the square root of 255 is not 0. So cache calculates return the wrong thing. I need to know why did that happen, right? Now, this is a nice little example of where the core file, that information is gone. I can't go back. I can't traverse the call tree, right, other than just going directly up. But this is time travel, so I can here. So here I go. So I'm going to hit this button here. We're going to reverse step into cache calculate so we can see why did it do what it did? Okay, so here we are. Look, it's returning. This is how cache calculator returns. It returns from the cache, returns the ith entry in the cache. I is 90. So I can have a look at that. What's the 90th entry in the cache? Tells me the square root of 255 is 0. So my cache is in a bad state, and that's why it's returned the wrong answer. And so now I need to find out, why and how did that happen? Well, it's a threaded program, and I can see here I've got a lock, and so yeah, that's suspicious, isn't it? I mean, that doesn't look obviously wrong, but maybe there's a problem. So what I'm going to do is back up, back to there. So this is just before this line of code executed. So at this point, the structure is locked. Well, it's still telling me the square root of 255 is 0. So yeah, it doesn't look like anything obviously wrong with threads. So, well, you know what I'm going to do is, I'm just going to clear that text off the screen. So we've got a command here available in the observatory called last, which is a little bit like a contraction of a concatenation of watch point and reverse continue, but I can go back to, it's a little bit more convenient. So I want to know, when did that entry in the cache change? So if I just go last gcache 90, it goes back in time to when that cache was updated, right? It's the line of code that most recently wrote into my cache. So okay, I'm writing square root adjacent and number adjacent into the cache. I'm actually midway through updating the cache, right? Because I'm at the beginning of this line 45. So I can just go forward a line now, the cache is updated. Yeah, that's the bad data, right? And if I step back to before that cache was updated, okay, so here the cache contains good data, right? The square root with integers of 40 is 6. If I step forwards, this is kind of like, action replay, watching sports on the TV. Watch the data here as I step this forward. Step. That's it. That's the corruption happening right there, writing into the cache. What gives? Why is it writing garbage? Well, it's writing number adjacent, which is -1, and it's square root, which is nonsense because you can't take the square root of -1. So why is number adjacent -1? That's not what I expected. Well, I can just ignore the numbers on the screen there. That's a bug we need to fix. But anyway, so I can do last number adjacent to find out why does number adjacent contain -1. Okay, it's here. It's being set number -1, and number here I can see is 0, right? So cache calculate got called. It did the right thing. Got called with a parameter, an argument of 0. It returned 0, but it updated the cache, and it updated one entry either side on the basis of some kind of locality of reference. And so one of them was -1 and was garbage. And my program didn't notice for quite a long time later. And when it tripped over the bad result and the assertion fired. So again, a small program, just suitable for a demo, but this is actually a canned demo of a real world, nice case study of time travel debugging, where one of our customers, Cadence, the chip design software people, they have very complex software, very long run times, and one of their customers was experiencing a problem where Cadence's software was crashing one run in 300 after about 8 hours of execution. And this is just a nightmare. And every time it did crash, it crashed in a different way. It was a major problem for that customer because it sort of was disrupting their flow. It meant they couldn't, tape out their chip, and phone wouldn't hit the shelves in time for Christmas or whatever. So Cadence had their software engineers on site with that customer for 3 months trying to get to the bottom of it, right? And they kept looking at core files. Every time they could load up a core file, there was a -1 where there should have been a pointer, but it was always in a different place. There was just nothing to go on. They couldn't find out where this -1 was being written into their data. And so that's when they turned to time travel debugging, and they ran it with Live Recorder, just set it up actually over the weekend, actually on a bunch of machines, just running again and again, because it took 8 hours and they only failed one run in 300. But when they came in on Monday, a couple of them had failed. And so they took one of those recordings, put a watch point on that -1, just like I did here, reverse back, and they had it nailed in 3 hours. So they went from 3 months to 3 hours. Actually, they went from infinite time, because they were getting nowhere after 3 months, to 3 hours. So that's a nice example of the power of time travel debugging. But I think if you integrate it with your CI, as I've just showed here, that's perhaps less high profile examples, but if you're routinely turning an afternoon debug session into 10 minutes, and you just keep doing that, the kind of compounding value of that is, I think, in some ways even more significant than those amazing sort of months or years down to hours cases. Those are the demos that I wanted to show. Let me go back to some slides. Oh, they're here, aren't they? Yeah.
There is a question.
Yeah.
So are there any similar tools like RR, but for bare metal systems? So like, do you have customers which use your system on embedded or like,
Right. So there are for bare metal, but now you need, because you don't have kind of the layers of OS and everything else to help you, you need the hardware to help you here. So Green Hills have a product called Time Machine, and Lauterbach have their debugger, which will work with, if your system has to support it. So you need an ARM chip with the embedded trace macro cell. There may be others. I don't know about other designs, but if it's ARM, it needs to have the embedded trace macro cell, and you need to have I don't know the details of this, so it's not my field, but you need to have sort of, I don't know, the JTAG sort of appropriately, that you can get at and things. But if you've got everything that you need, you can then get the Lauterbach debugger or the Time Machine debugger from and Time Travel Debug at the hardware level. Yeah, and it's very good, by the way, and it runs like pretty much full speed, and you get full kind of visibility. So there are different flavors of it. So depending on exactly which kind of embedded trace macro cell you have, I think you don't necessarily get the data, but if you've got the kind of top of the range ones, you do get the data as well as the program counter information. And
there's another question. Can we use this tool on other custom Linux distributions?
Yeah. So So I showed two tools, right? I showed RR and I showed Live Recorder, which is my own company's tool. RR is a little bit more kind of, it has requirements about, has to have access particularly to the performance counters. It needs SE comp and a few other things of the kernel. So it does have quite kind of strict requirements. But if all those are there, then, and you've got a suitable CPU, so you need an Intel or one of the very recent AMD CPUs that supports performance counters with the appropriate kind of precision. But if you've got all that, then yeah, it'll work. Our own product, Live Recorder, is a little bit less kind of fussy about where it runs, because it doesn't rely on those hardware features, or in any advanced kernel features. So that will run on most, even quite cut down kernels. And then the other really nice thing is you can take these recordings and replay them on a completely different system. You can take it off a customized embedded Linux and replay it on your Ubuntu running on your laptop, for example. So yeah, I talked about these earlier, to the earlier question, the different kind of flavors that are available. So we just saw Live Recorder in the demo there, and we saw RR as well. I showed very briefly GDB Process Record. I talked a bit about Microsoft's time travel debugging solutions, and also there's a company called RevDebug, just Java for Windows, and I mentioned replay.io as well for that sort of front end JavaScript time travel debugging. I'm just going to go on to just talk a little bit. Well, just before I do that, actually, yeah. So time travel debugging is, I think that's kind of the terminology that everyone's kind of converging on this. So the concepts here are kind of new, and everyone's been kind of settling on what to call it. So over the last few years, people put it reversible debugging, bidirectional debugging, replay debugging. I think the world is kind of standardizing on time travel debugging as the right term for this. They're all basically the same thing. So let me just talk a couple of minutes about how we implemented this and how tools like RR and Microsoft TTD and others actually work, because it's quite, I think, quite interesting, technical challenge, right? So as I said earlier, debugging is about what happened. So I'm going to step back in time, right? But another way of saying, perhaps a slightly more precise way of asking what happened, is what was the previous state? I've got my program, I've stopped my program inside the debugger. and I want to know what the previous state of it was, like the previous instruction or line of code they executed. So how do I do that? How do I go back to the previous state? Well, there's two ways that you can do this, right? One is I can just save the previous state, so then I can restore it. Now, clearly, I'm not going to like save the entire program state for every single instruction that executes, because that would just be enormous and completely impractical. But I could just save the delta, right, which is a very common technique, sort of MPEG style. I'm just going to change what changed between this, store what changed between this instruction and the previous instruction, and then I can reconstruct those previous states by going and applying those changes that I've saved kind of in reverse. And that's what GDB process record does. It's still really slow and consumes loads of memory, because you've be back to this thing that the computer's doing billions of things every second. So if I'm saving, even if I'm just saving, this registered update or every instruction, I mean, something's going to change every instruction, right? Otherwise, think about it. Otherwise, I'm in an infinite loop, just branching back to myself. So something's going to change every instruction. So that's going to be 4 bytes. I mean, at least several bits every instruction. So billions, gigabytes of data saved per second of execution, and also it goes really slowly because there's just a lot of work to do between every single instruction. So saving it works, but it doesn't scale really is the problem. So better to recompute it, right? I want to work out what my previous state was. The trouble is I can't just apply logic in reverse. That doesn't work, right? If we've got a statement like this, that's a reversible statement. If I've just executed that statement and A contains 42, then I know that the previous state, A, contained 41, right? But that's not a reversible statement. If I've just executed that statement and A and B both contain 42, I have no idea what A was before, right? That information doesn't exist in the universe anymore. But what we can do, because we can't run computer programs backwards, but what we can do is rerun them. We can run them again and try and make sure that it does the same thing the next time I run it, right? So we use this kind of snapshot and replay technique. So when in the demos, I'm going back a line of code, what actually is happening is going back to a snapshot. I'm playing it forward to just, right before where it previously was. And that gives me the illusion of stepping back through time. And this works because computers are naturally deterministic things, right? If I take a program and give it the same starting state and give it the same inputs as it runs, it will always do the same thing. This is why random numbers are difficult to generate, right? Because the catch is that programs computers are deterministic, except when they're not. Except when I've got any kind of I just said that throwaway statement. I've got to feed it the same set of inputs as it runs. And so that might be inputs from the network, it might be from the user, it might be timing things. There are other non-deterministic stimuli, particularly around threads and thread scheduling. That's particularly challenging. Might be reading from shared memory. There are some instructions that are non-deterministic. If I add 2 numbers together and they're the same 2 numbers, I always get the same result. If I do a read the timestamp counter, I get a different result each time. Any kind of system call, I'm likely to get a different result. In fact, if I could predict the results of a system call based on what my program state was, then it probably shouldn't be a system call, right? It should be a library function. So I've got these certain things which are a real minority. They're like 0.001% or something of the instructions. Most of the instructions that a program executes are, add these 2 numbers together, move this thing over here, jump over there, and they're all completely deterministic. But just the very, very few that are not, we need to store those in an event log, and then we can replay them. And as we do so, we can guarantee the program follows exactly the same path. And that's the trick to this. This is how most of these tools work, some variation on that. So we need to store all these non-deterministic events, which how many there are will depend entirely on what your program is doing. If you're calculating pi to 1 billion decimal places, then there'll be very few external events that you need to store in the event log. If you're reading, uncompressed high definition video, then there's going to be a lot. So it depends entirely what the program is doing. But typically, the recordings that get generated, kind of just a rough kind of rule of thumb, typically it's like a few megabytes per second of recording. So it's pretty efficient, right? And these recordings tend to be on the order of 1 to 10, 1 to 100 gigabytes is probably the normal range. I see them much smaller. I see them much larger. But that's kind of typical kind of range. So they're quite, you're probably not going to put these as an email attachment and send them, but they're pretty manageable things. Just a quick plug for my GDB Watchpoint tutorials. A whole bunch of like 5-minute, 1-minute videos on little tricks and tips with just regular GDB. So hopefully that's useful for at least some of you. Any more questions?
Yeah, that'd be a good question if there's any more questions. I don't see any more questions in the chat right now, but let's give people some time to type. Thank you, Greg. It was a great presentation.
Thank you very much.
And so, so if you have any questions, type them in the chat, and otherwise Greg is available on LinkedIn, and probably if you post later questions into the chat, like if you actually watch the video and mention Greg probably will come around and answer your question on LinkedIn. And so far, I don't see any new questions in the chat. So that was an awesome presentation and live demo. Not easy to do. Thanks for doing. And if there's anything else.
Yeah, no, it was good. Thank you for letting me talk about this stuff. And there were some nice questions as we went as well.
Yeah, one thing. One person asked about courses online, and that might be a good question. Like, does Undo have courses or like video series and etc. like where you learn more about this?
Yeah. So we do, as you can see here, undo.io resources GDB Watchpoint. So there's a bunch of stuff there. That's on regular GDB, a whole bunch of training materials on time travel debugging as well. So yeah, there's a bunch of stuff on the website, and we do also do training to companies of sort of in-person training sessions as well. So if you're interested in that, then probably the best thing is you can just email to sales@undo.io, and they'll connect you with the right person.
Okay. There's right now a question in the chat. How effective would it be in MT? And I think MT is multi-threading.
Very. Yeah. I mean, the second demo I gave, that was a multi-threaded program, right? It wasn't a multi-threaded bug, but it was a multi-threaded program. One of the main use cases for this is diagnosing difficult race conditions, right? The thing that makes bugs difficult is, well, there's I think there's two axes to difficulty. So there's how long is it between the bug itself and me noticing the assertion failing or whatever, on one axis, and on the other axis, it's sort of how repeatable is it? Does it always fail in the same way, or does it fail in a different way each time? And when you get a kind of combination of those things, long time between the bug and the kind of notification of the failure, and it's non-deterministic, it's non-repeatable, then those are really, really hard to debug, right? This is where printf really lets you down here, because it gives you a view of what one run of the program did, but you add new printfs and the program does something different. And so time travel debugging is super useful here. That's really where it's most powerful, where the bugs are the hardest. And race conditions are that's kind of true of almost all race conditions, right? They're almost always non-repeatable, and you usually don't notice something's gone wrong until sometime afterwards. So so diagnosing race conditions is like one of the main use cases for time travel debugging, I would say.
And one question I was just wondering about, you're writing a time travel debugger. Have you used your own time travel debugger when writing your time travel debugger?
All the time. Absolutely. Yeah. So big fan of the dog food, right? And I showed you that was the second demo I did. That was actually our internal CI system, and you could see, we automatically generating recordings when tests fail, so that our engineers can step through. So yeah, it might slightly make your mind, you to sort of can be a bit of a head fuck, because you sort of I'm debugging the debugger, but yeah, happens all the time. And in fact, we even have, this is less common, but sometimes we've found that our own code is actually quite a good test case, right? It does a lot of stuff, shared memory, and it's asynchronous, and there's multi-threading going on, and generally it's a very good kind of test case workload for our own software, right? So it took us some time, took us quite a few years before the technology was advanced enough that we could eat our own dog food, right? It was kind of one of the last programs that we could record, because it just does everything. And at that point, it was, that was that kind of just massive improvement in our internal productivity when we could debug our own stuff. And we occasionally you do occasionally get a problem where we've got a problem in our thing, so we record live recorder, and the recording of live recorder goes wrong for some different way. Like, this happens much less often these days, thankfully, but still very occasionally can happen. So there have been occasions where I've got a recording of live recorder that's recording live recorder. I've never had to go more than three levels of recursion, but in theory you could keep going.
Okay, that was an interesting story. And with that, I think we're through, and Greg might have the next meeting at the full point. So thank you for your attention. Thank you for coming, and thank you for just making this possible. The first time we actually live on LinkedIn was a guest. Thank you, Greg. And
that's great.
So if you have any more questions like this, post them later in the chat, and Andu probably will take care of that. And with that, we're going to end the live stream. Thank you to Andu, thank you to Greg, and all the others in the chat.
Thanks, Jens. Thanks, everyone.